Let us start today's work. Am I audible? Hello? Hello? Am I audible? Hello? Hello? Am I audible? Please answer. Problem. Hello? Am I audible? Hello?
Yes, sir.
Huh?
Good morning, sir.
Good morning.
Good morning, sir.
Hmm. You are late. Let us start. Today we'll discuss different relation between the different coefficients of the modulus of different the relationship between different modulus of elasticity. And in order to do so, let us quickly recapitulate what we have done so far in terms of modulus of rigidity, etc. Here we have defined that we have three coordinate axes, OX, OY, and OZ, which is originated from the origin O itself. And these three axes are coincides with the principal stress axis. Means OX may be major stress, OY may be in between, and OZ is the minimum stress itself. The specialty of this specialty or the benefit which you are getting from absorbing and coinciding this with principal axis is that we don't have to take into account any shear forces, as we have seen in our earlier classes that on the principal plane where the principal stress or major stress or minor stress are acting, there is no shear stress exists, and the principal strain also there is no shear strain or no deformity of your object is available is possible. So thus we are starting with our discussion with three rectangular coordinate axes x, y, and z with origin at O, and all three are coordinates. All three are coinciding with principal axis, principal stress axis. Now we will first imagine isotropic body, means a body whose all whose don't have any directional change of its forces on a particular point itself, which means for a particular point, stresses are same in any direction itself. That is called isotropic body. So here we just consider another orthogonal section OX dash, OY dash, and OZ dash with the same origin at O here, but X is shifted to a certain distance from OX, same is Y is shifted to a certain amount by OY, and OZ is uh, shifted to a certain amount by OZ. As both these OX, Y, and OZ and OX dash, OY dash, and OZ are orthogonal planes, which means their mutual angle will always be equal to 90 degrees. So whatever change the OX dash made with OX, OY and OY dash and OZ dash will have the same angular change with OZ and OY. As we see, as we are considering isotropic body, due to this change in angle, there will the strength and other things will not change as per our equation itself. But there are certain changes definitely due to the change in the direction cosines of all these things, all x, y, and oz itself. And what we find that first we make the direction cosine clear. Say the direction cosine of ox dash after when it's changed from ox will be nx1, ny1, and nz1. Means with the change in ox has always have a change with x axis with y axis and oz axis, and the angular change and cosine of the angular change thus formed is given as nx1, ny1, and nz1. Then we consider oy dash, and whose direction cosines with x-axis, y-axis, and z-axis become nx2, nyz2, and nz2. And we'll take into account oz dash, but not here or afterwards. We have seen as ox dash and oy dash are mutually orthogonal, or mutual angle is become 90 degree. So nx1 point into nx2 plus ny1 into ny2 plus nz1 into nz2 means the reaction cosine of these two reaction cosine here, these two reaction cosines here, and these two reaction cosines here. If we multiply these two each other, we know that as per the definition of reaction cosines, this value will be equal to 0. This relation we will use afterwards. Now, let us consider a normal stress, the sigma x dash, which is acting in the Cartesian coordinate axis ox dash, oy dash, and oz dash, and it is acting as a normal force as on a plane, whose resultant whose normal plane who has a normal equal to n, and who has a who is intending at an angle with ox dash and y dash and oz dash axis, and which is equal to in terms equal to nx1, nx1, ny1, and nz1, etc. The resultant stress vector on the x plane in terms of sigma 1 means the principal strain or major strain, in between strain and minimum strain. In terms of sigma 1, it will be equal to nx1 into sigma 1, ny1 into sigma 2, nz2 into sigma 2. As we know that the direction cosine with the angle x, direction cosine of x-axis, ox dash axis in terms of oxy is equal to nx1, ny1, and nz1. So as we know the direction cosine, and we can think this sigma 1 and sigma 2 and sigma 3 as the hypotenuse, and in between angle is 60 degrees. So the coefficient of this sigma 1 with this sigma 1 multiplied by the direction cosine will be equal to the tau x tx, that is not y but is actually x, ty, and tz. These are equating each other like this, because again I'm telling you the sigma 1, 2, 3 are along ox axis, y axis, and oz axis, and with this we know the direction cosine of ox dash with ox axis, with ox, y, and oz axis are tx1, ty1, and tz1. And that's if we assume ox, y, and oz as hypotenuse, and then use this in between angle between ox dash and ox dash and ox dash and y, etc. Then by multiplying sigma 1 into ox dash, we'll get the component of the resultant stress along x-axis, ox dash axis, y dash axis, and oz dash axis itself. Now these components are in x dash, y direction. The normal stress in the x dash direction is obtained. The normal stress in this x dash space is thus obtained here with this formula sigma n, or sigma x dash, we can say, is equal to nx1, so sigma 1, ny1 by sigma 2, and ny2 by sigma 2 by multiplying nx1 by sigma 1 by nx1 again, this by ny2 again, and this by ny2 nz2 again, because it's also now intending an angle equal to the direction cosine of the concerned element itself. Thus we got sigma n, and in the similar fashion we got tau x1, whose where we have to multiply sigma 1 nx1 into ny2 nx2, and sigma y and sigma y y2 and ny2 is equal to ny2 multiplied by ny2, and similarly with this here for terms here. On the same line, this epsilon 1, epsilon 2, epsilon 3 are the principal strain itself, and we have already deduced in XYZ normal strain will be similar fashion, nx1 epsilon 1 ny1 square epsilon 2 and z square epsilon 3 itself. It was the from plane strain analysis itself. Now, in 4, 5, 5. Now, we know from our strain analysis, the shear strain gamma x dash y dash is obtained from this formula, which we have reduced like this. We have two straight lines, one originated from the same origin, say P, one is PQ and one is PR, say PR, and in between angle is equal to theta itself. Sometimes it happens due to the action of the action of external force is this PQ and PR with internal angle theta is distorted and moved in a different position with a position like P dash Q dash or and P dash R dash with the in between angle lifted to theta dash itself. And we know that our shear strain is given as the angle tan theta, or it will, as it is extremely small, equal to theta dash, which is given by this formula gamma x1 x dash y dash, which is equal to tan theta or equal to theta, is equal to 1 plus 1 by x dash and y dash, the strain along y axis and z axis, y dash x dash axis and z axis, nx1 and epsilon 1, nx2 itself, epsilon 1, epsilon 2, and epsilon 3 have the principal strain itself. And here nx1, nx2 multiplied nx2 plus ny1, ny2 plus nz2 into nz2 itself. As we know, epsilon x is too small, epsilon is too small, and epsilon y dash is too small in comparison to 1. So its effect is negligible. So we can have full term equal to 1 itself. We have just reduced that nx1 multiplied by nx2 plus ny1 minus ny2, nz1 multiplied by nz2 is equal to 0 itself. So hold this thing will equal to 1 and this is equal to 0. This particular equation will reduce to y x dash y dash here equal not plus but equal to nx1 nx2. This full function will be written here, which is the value of the shear strain. Now, from equation 4a, which was like this, sigma 1 means principal stress along, say, x-axis. X-axis is 2 in lambda into delta plus 2 into mu into epsilon 1. And lambda 2 and sigma 2 and sigma 3 has the same value in terms of epsilon 2, epsilon 2 and epsilon 3. Thus, we substitute value of, if we substitute this value of sigma 1, 2, 3 in the equation into the equation 6b like this, which was stated here as tau x dash y dash into nx1 nx2 sigma 1 ny1 ny2 sigma 2 and nz1 nz2 sigma 3 itself, where you put, if you put the value of sigma 1 sigma 2 and sigma 3 from that equation I just have told you earlier, then this equation tau xy will become nx1 nx2 ny1 ny2 nz1 nz2 multiplied by lambda into delta plus 2 into mu into epsilon 1, lambda into delta 2 mu into epsilon 2, and lambda into delta 2 mu epsilon 3 itself. Now what happens here? So if you again simplify, then 2 into lambda, lambda into delta is equal to this particular value plus this value and this value. This is total here, and 2 into mu is given as multiplied by 2 into mu is multiplied by this nx1 ny into in terms of f multiplied by f sub 1, ny1 y2 multiplied by f sub 2, and yz2 and z2 multiplied by f sub 3 itself. Thus, from these two equations, we can say these are more or less. Here we again, this equation is equal to 0 itself, because we know this one nx1 nx multiplied by nx2 and y1 multiplied by nx2 and z2 multiplied by nx2 is equal to 0 itself. So, and this value is equal to this total value starting from mu1 to here is equal to given by gamma x dash y dash into 2 itself. So what we have, tau x dash y dash is equal to gamma x dash y dash itself. The equation 8 now relates the rectangular straight components tau x dash y dash with rectangular shear components gamma x dash y dash. We can compare this relation with elementary sector 1. We say that mu is the radius of rigidity, usually denoted by g. So here this mu is actually our modulus of rigidity, which is we noted that earlier as g. Now taking the angle OZ, direction cosine nx3, nyz, and n3, and right angles 2x and OA, and we'll get in the similar manner just we have told you, we'll get the following relation like this. This is nx, ny dash, and z dash, tau z dash, and for the next time, stop share. Then it becomes the form like this, and similarly following the equation 7 and b, and for other rectangular components, we are getting this value equal to tau is yz and y tau x. So it's equal to 2 like this. From the equation, we'll get the value equal to sigma y (17) tau x y gamma. First, sigma y and sigma z, we have got these two terms, and then we got tau yz, I dash z dash, then yz z dash is same here, and term z dash xx is same here, and the following, and gamma x1, gamma yz is given in the similar manner to nx1, nx2, nx2 and nx3 like here, and sigma tau f psi f6 this, and f psi z is this like this, and gamma is like this, and gamma x dash y dash, just 1 second. Bulk modulus. That's another widget. Then we have these relations in terms of yz, gamma yz, and gamma zx itself. Thus, and from equation 4b cell c, where we are getting the value of sigma 1 itself, 4 and sigma x is sigma 1, 2, 3, and putting the value of lambda as well as epsilon, putting in the value lambda x1, this is become exx itself. Lambda y is y itself, lambda z is equal to ez itself. And thus, similar to equation 8, we have tau x y dash z dash and mu tau y z among gamma y z and vector mu gamma y z itself. Thus, we have the shear forces in all three directions respectively. Here in the similar manner, we have calculated the earlier. What we have here, just 1 second. What we have here, first of all, we have reduced the value of tau x y z in terms of nx1, nx3, nx1, and sigma 1, sigma 2, and sigma 3. This shear strain component we have reduced earlier itself, and then as epsilon 1, epsilon 2, and epsilon 3 at principal strain, we are calculating the value of epsilon in x y dash z dash itself, and gamma y z we have got the relation between equation 36, where we have got and put the from the simplification we have got this particular value itself, gamma y z I should just find the zero. This is actually gamma, not y. This is so we have got three relations here given in terms of bulk modulus here, tau xy, xj, tau xz, etc. Now, first of all, equation 10b means 12abc relates the three rectangular stress component with 6 rectangular strain components, and in this only 2 elastic constants, that is Lami's constant, is given as lambda into gamma, and lambda and mu is equal to more or less equal to the modulus of velocity g itself. Now what happens? Let us go for the next page. That is page number 7. So what is the bulk modulus itself? Now, if we add the equations 11 to C like this, that is sigma x plus sigma x dash plus sigma y dash and sigma z dash. If we add them together, then what we'll have found that right hand side is 3 into lambda. What we have sigma x dash, which is equal to 2 into lambda and x1 into lambda and x1. If we put the value of sigma x here, and we represent sigma x dash in terms of sigma 1 plus sigma x dash is lambda into delta plus 2 into mu plus xx dash here, and then sigma y dash is similar, sigma z dash is similar itself. And now, if we add them together, they will found 3 lambda into delta plus 2 into mu epsilon x dash y dash plus epsilon y dash z dash plus epsilon z dash z dash. Observing this, this is given as sigma x dash 1 plus sigma y dash sigma z dash is equal to L1 is equal to sigma 1 plus sigma 2 into sigma 3, which is the latest variant of stresses itself. Now, what happens here? Epsilon x dash, epsilon y dash, double dash, epsilon z dash is equal to J1 is equal to epsilon 1, epsilon 2, C. This second variant of stress itself. Now, this equation itself can be written as in the same manner as this is the sigma 1, 2, 3, and his epsilon x is replaced by the J1 or delta itself. And similar x dash y dash z dash is in the same manner we are having this same thing here. And L1, thus L1 is equal to 2 into lambda, 3 into lambda plus J1 itself. Lambda plus mu L itself. So these are all, both this equal to L1, and so you can safely put here, and both this is equal to either J1 or lambda. So you can simply put it as J1 itself, where delta is the volumetric strain. The definition of the bulk modulus is K is given as pressure by volumetric strain is equal to internal pressure divided by delta itself. And if you say the internal pressure P is equal to sigma 1, which is equal to sigma 2 is equal to sigma 3, then this equation becomes say sigma 1 is equal to 3 into P then equation 13b is put it to 3 is equal to 3 into P at 3 lambda plus 2 sigma into mu itself. Now 3p by delta is 3 lambda into mu, lambda plus mu itself, and equation, thus this equation 14 will become K into 1/3, 2 into lambda plus 2 into mu. Thus the bulk modulus for an isotropic solid in relation to Lemming's constant through equation 14b. These are the Lemming's constant, this one and this one. And you see the Young's modulus and Poisson ratio from equation we have delta can be equal to delta 1 plus 2 divided by 3 lambda plus 2 mu. From this equation 13b we have equation 13b. If we just put it like this, lambda is equal to 3 plus 1 plus 2 plus 3 divided by 3 into lambda plus 2 into mu. Now, if we substitute in 4a, where sigma 1 is given as 2 into delta plus 2 mu into epsilon 1, then in case of delta we put this value, so lambda multiplied by this sigma divided by sigma 1 plus 2 plus 3, the other 3 lambda plus 2 mu plus 2 mu plus epsilon 1 itself. Stop share. In the similar fashion, or delta 1 or epsilon 1 itself become epsilon 1 in terms of epsilon 1, that relation will become lambda into 2 plus mu 2 lambda into plus delta 1 minus 2 by lambda delta 2 plus delta 3 itself. So from elementary strength of material we know epsilon 1, the elongation the strain longitudinal strain is equal to 1 by E multiplied by sigma 1 minus gamma sigma 2 plus sigma 3, where EI is Young's modulus, V is the Poisson's ratio itself, and comparing this with the question 13, what we'll find or equate them, we'll find that uh, E is here, F sub E is become equal to mu into 3 lambda plus 2 mu, thereby lambda plus mu itself. Plus V, and V is equal to lambda is equal to 2 plus mu plus 2 lambda, mu plus epsilon. Thus, we have got the two relation between E and lambda itself, E and gamma with terms of lambda and mu itself, and bulk modulus in terms of lambda and mu itself, or Lami's equation. Question 15 very much. Now, let us go through the relation between elastic constant itself. We are familiar with the Young's modulus E, Poisson's ratio gamma, and shear modulus or modulus elasticity G, etc., and bulk modulus K itself. But there are only two are independent, means only gamma as well Young's modulus and bulk modulus are taken as independent because they have no relation among themselves. But G and K are can be expressed as G is equal to E by 2 plus gamma, 2 plus 1 plus mu, K is equal to E by 3 into 1 minus epsilon itself. This is shown from an isotropic material itself, who has this whose properties it doesn't change directionally. 36 constants are reduced in generalist, is given in generalist Hooke's law, and it is reduced in two independent elastic constants. This constant are Lami's coefficient, lambda and mu itself. The second coefficient mu is same as the Lorentz elasticity G. In terms of this, other elastic constant can be expressed as, which is given here, E is equal to mu into 3 lambda plus 2 mu and gamma into lambda plus 3 plus mu. K is equal to 3 into lambda plus 2 mu divided by 3, and G is equal to mu is equal to lambda is into V into E divided by 1 plus 3 itself. Let's K is equal to this, and G is equal to mu, then lambda here will have V into E divided by 2 plus gamma plus 1 plus mu itself. It can be observed that from this above equation 17 means here that the bulk modulus is to be positive always, so the value of Poisson's ratio cannot be less than exceed equal to more than half, because here if it's more than half, this thing will be negative, and this lambda cannot be negative itself or cannot be equal to half itself, because that will, in that case, lambda will become equal to infinity itself. So this is the upper limit for V is equal to 3 is equal to 3j and K is equal to infinity itself. Stop share. Now, a material having the Poisson's ratio equal to half is known as an incompressible material, means the volumetric strain for such a isotropic material is equal to 0. For easy reference, we can recall the equation with stress and strain so that it has been obtained so far. Instance of principal stress and principal strain, we have got this relation F sigma 1 lambda plus mu equal to 2 into mu into epsilon 1 lambda into delta, 2 into mu epsilon 2, and lambda into delta 2 mu epsilon 3 itself, where lambda is equal to epsilon 1 plus epsilon 2 plus epsilon 3 is equal to J1. Thus, epsilon 1 equal to epsilon equal to this formula, and epsilon 2 is equal to this formula we have discussed earlier, and epsilon 3 becomes this like this. In terms of rectangular stresses and strain components referred to an orthogonal coordinate system Ox, Y, Z, that we have all 1 or 2 and 3 are replaced by X, Y, Z, Exx, Eyy, Ez, where delta is equal to X plus Xx plus Eyy plus Ez is equal to gamma. Tau Xy mu into gamma Xy. Tau Yz gamma mu into gamma Yz, and tau Yz is equal to gamma into mu. Thus, we can have from these three equations, this is converted into epsilon Xx, epsilon Yy, epsilon Zz, like this here. Go for and gamma xy 1 by mu tau xy, gamma yz 1 by mu tau yz, and gamma zx is the same. In the preceding set of equations, lambda and mu are Lami's constant in terms of the more familiar elastic constant E and V. The stress strain relations are become epsilon xx, sigma x, sigma y, and sigma z are these given us with delta x, y, z at x, and they are replaced as they form like this: lambda j1 plus 2 into g lambda xx epsilon y lambda j2, 2 into x lambda xxy, and sigma y lambda j2 itself tau xy g, and we replace mu by g and g, and xx we are replaced by e and gamma, and like this itself. Gamma xy like this, exx, uyy, and ezz itself.